Next topic is coupling and load capacitor effects in the common emitter amplifier circuit. That is the next topic. In the last lecture we discussed the input coupling capacitor alone. Here we are going to see coupling and load capacitor. So that means we are going to derive two cutoff frequency. That is for a coupling capacitor we will be deriving FL, for a load capacitor we will be deriving FH. So what is the tau function? What is the tau function with respect to FL and what is the tau function with respect to FH we are going to derive. So we can write the tau function for FL as tau s, because your coupling capacitor is going to be series with your input side, right? Similarly, if you take for FH, your load capacitor will be going to be a parallel, so I can write like a tau. Okay, so we will go for the very basic. So before we are going to the important part, let me start with the basic. So when you go for the mid-band frequency, your coupling and bypass capacitor will become a short. So you can see you have a ranges of frequency, right? In the ranges of frequency, for the ranges of frequency, you don't have any limitation in the gain, right? So because the coupling and bypass capacitor acting as a short, and stray and transistor and load capacitance acting as a open element. When you go for the low frequency, you have a FL, right? So when frequency is less than FL, you can see that the limitation in the gain, because the coupling and bypass capacitor will be included in the equivalent model. That will be limit your gain down. That is a roll-off function because of your R and to C value that we are going to find in this problem, in this derivation part. Okay, during that time when you are finding for low frequency part, your stray, transistor and load capacitance will be acting as an open circuit. When you finding for FH cutoff frequency, your stray, transistor, load capacitance will be considered in your equivalent model and will limit your gain. During that time, your coupling and bypass capacitor will be acting as a short circuit. Okay, that is a theory you want to understand. Okay, now we will go for the very important part. See, this is your circuit. In this circuit, this is input coupling capacitor, that is CC. CL is your load capacitor. See there, C will limit your gain in the lower frequency. So that is FL. Because of CC, if there is a limitation, means that we need to say as a FL. So you have a limitation in the higher frequency. It is because of your load capacitor, that is FH. Okay, so you can see like your CC is something like a high pass filter. It will be acting like a high pass filter, right? When you go for this circuit, it will be something act like a low pass filter. Okay, so that means it will allow the low frequency and it will block the higher frequency. Okay, the combination of two circuits that we are going to discuss now. So the CC will be contribute to limit the gain in the lower frequency. Okay, and CL will be contribute to limit the gain in the higher frequency. So you know that when CC is connected in series, we used to say as a high pass filter, because it will allow the higher frequency and limit your lower frequency part. Similarly, when you go for the CL, it is something like a low pass filter. That means it will allow the low frequency and higher frequency it will limit. So that is a basic that what you studied. Okay, now from this we are going to draw the small signal equivalent circuit. Very simple. First what you want to put is, first put your base, collector, emitter. Here you can put it as an emitter. So now put the mathematical model. Between base and emitter you have a R pi. So R pi. The drop across this R pi is a V pi. What is the gain in the collector terminal? GM times of V pi. That's all. The mathematical model is over. So completed. So this is the transistor part. The transistor part is over. Now below emitter you have a RE resistor. So that RE resistor is given. So emitter current is nothing but the sum of your base current and collector current. Okay, here I am taking as a Ri. So Ri means the resistance in this part, that is Ri plus 1 plus beta times of Ri. That is a reflection rule here. So that we studied in the last slides, right? So here now this internal part is over and this also over. Now I will remove this DC supply. I will remove this both the DC supply, this one and this one. So what happened, this when I remove this, R1 will come to parallel, right? R1 will come to parallel, you can see. I want to find what is the impact of input coupling capacitor, so I consider in the equivalent model. So then RS, then VA. Then similarly in the right side you can see the RS will come to the ground. So RL already disconnected to ground, so CL is connected to the ground. Okay, so this is your equivalent model for this circuit. I hope it was clear. Right, now I have increased the size for your more understanding. You can see here like this is an input coupling capacitor, this is a load capacitor. This is a corresponding resistance are in parallel. Here in the series capacitor, this resistance are in parallel and this resistance are series with this capacitor. Right, so that is very important. Okay, that is the idea I want to get. Now let me erase this. Okay, so now very interesting part. Now we will see the lower cutoff frequency and upper cutoff frequency. What is that? Already we know. This you again. So this is your frequency versus gain, right? So this is your lower cutoff frequency and this is your FH cutoff frequency. This FL limitation gain in the lower frequency because of your input coupling capacitor. FH, the limitation of gain in the higher frequency because of your load capacitor. What is the roll-off function I want to find? So that means very simple, by looking the circuit itself we can identify what is the roll-off function. That is the thing you want to understand. So FL equal to 1 divided by 2 pi tau S. Only this capacitor is connected in series, right? Only for understanding that I have just given tau S. What is a tau? Is nothing but a product of R into C. See, very simple. Now look at the capacitor. Now look at the capacitor. So for this capacitor, this RS is series. Okay, you can consider VA as a 0. Okay, you can consider as a VA is 0. So for this capacitor, this, see, you can clearly observe, for this capacitor, this RS is series. That means RS plus this whole part is going to be parallel, right? It is series only, na? See, it is something like this. So what I am trying to say is, it is something like this. This is a C1 capacitor, CC capacitor. This is RS, and this part is R1 parallel to R2 and R2 parallel to R pi plus 1 plus beta times of RE. So for this capacitor, you have a this resistor and this resistor. This is in the left side and this is in the right side. So that means this is series. So that's why I put RS plus R1 parallel to R2, R2 parallel to R pi plus 1 plus beta times of RE into your capacitance CC. So this one I can take it as a RI. You can see, right? So that means I can write it as tau is nothing but a RS plus R1 parallel to R2 parallel to RI into CC. That's all. So now very simple. So you got this FL. Now we want to find for FH. Okay. So by looking the circuit itself, we can identify this tau function. Now we will identify for FH. So 1 divided by 2 pi tau P, because capacitor in parallel. So you know that when capacitors are connected in parallel, it is something behave like a low pass filter. See, for this is considered the equivalent model. So based on the frequency, the resistance will be there. You can consider as open circuit. So if you see the resistance part, for this, you can see all are connected in the series. Similarly, you can consider VA is 0 here. VA is 0, okay, and we can proceed here. So it will be considered as an open circuit and the resistance will be RC parallel to RL. So what is the tau P? Tau P will be RC parallel to RL into your CL. For what is the tau S? Tau S is RS plus, because it is connected in series. See, by looking itself you can understand it is series. So R1 parallel to R2 parallel to Ri. That's all. What is the capacitance here? Cc. What is the capacitance here? Cl. That's all. So that only here explained you clearly. What is FL? FL is a lower corner frequency 1 divided by 2 pi tau s. What is the tau s? They have derived Rs plus R1 parallel to R2 parallel to Ri into Cc. By looking the circuit itself, we can identify clearly. Ri is nothing but R pi plus 1 plus beta times of Re. I said we are finding you need to consider signal source equal to 0 and the equivalent resistance will be with the coupling capacitor will be Rs plus R1 parallel to R2, R2 parallel to Ri into Cc. Similarly, if you find for FH, what you will get? We will be finding tau p equal to Rc parallel to Rl. For this capacitor, will be considered as an open circuit. Okay, while you are finding with respect to different ranges of frequency. Okay, so the Rc and Rl is parallel to this capacitor. By looking itself, you can understand, right? Here you can see it was series, here it was just parallel. So the tau p equal to Rc parallel to Rl into Cl. So your formula will become 1 divided by 2 pi Rc parallel to Rl into Cl. So this is a different concept you want to understand. So Cc is your input coupling capacitor, Cl is your load capacitor. So the load capacitor work dominantly only in the higher frequency. Okay, that will be included in your higher frequency model. Okay, so higher frequency model, right? When you see the input coupling capacitor, it work only in the lower frequency, it will not work in the higher frequency. So that is the concept you want to understand here. So you can see here the midband gain is a like a more high, right? You can, it's a more apart. You can see here like your response will be something like this, right? So this is your FL and this is your FH. So what they are saying is the two corner frequency are far apart. The gain will be maximum value in the frequency range between the FL and FH. During between the range of FL and FH, we have a stable gain because the reactance is 0 in that point. That is called midband gain. So how I can find, if I want to find a midband gain with respect to that part. See, to calculate the midband gain, so what is the consideration is, see, I said clearly in this starting point. See, the coupling will be acting as a short and load and transistor stay capacitance will be acting as a open. This concept you want to use now. Okay, see, I am going to consider your coupling capacitor as the short, and this will be acting as a open. That's all. Now you write the formula. What is the formula for voltage, output voltage? V0 equal to I into R. What is the output resistance when you open circuit this part? Rc parallel to RL. So I hope this is clear. Rc parallel to RL. What is the output current? IC. So conventional current direction. What is the IC? Is nothing but the GM V pi. That is a dependent current source. So GM V pi. So we know that IC and load current both are opposite. With that consideration, I am introducing minus here. Minus. So it becomes V0 equal to GM V pi RC parallel to RL. Up to this you are clear. Now you know that V pi. What is a V pi? V pi will be product of IB into R pi. That is clear. Okay. Now we will see what is the IB. So please remember, we are finding what is the mid-band gain. Mid-band gain. During that, coupling capacitor acts as a short and your load capacitor acts as a open. See, now I am going to find what is IB, right? So during that time, mid-band, it will be considered as a short. It will be short, so it will not include in your current equation. Okay, so IB equal to II, that is a current source. What is that you want to find for this part? That means you want to look the opposite resistance. What is the opposite resistance for this resistance part? This one, right? That is R1 parallel to R2. See, divided by R1 parallel to R2 plus this Ri. That's all. So it is something like a R1 parallel to R2. So here R1 parallel to R2. Here you have a Ri. So here I want to find what is IB. So what is the formula? Current source is IA. So IB equal to opposite resistance, that is R1 parallel to R2 divided by R1 parallel to R2 plus Ri. That's all. You will be getting this equation. That's all. See, only thing is, please remember this coupling capacitor is acting as a short circuit. That's why I am not adding in your equation. See now, if you write for IA, now you want to find IA, right? What is IA? So IA is this part. So that is V by R. V by R. What is your V here? VI. What is your resistance? RS. RS. Okay. Plus. Okay. When you are finding this part, you have to consider as a series only, right? This will be series. RS will be series with this whole part, right? So because you have this VA, right? You have a VA. So this RS will be series with this whole part. So RS plus will come because it is series with this whole part. See, IA equal to VI divided by this RS is series plus because this whole part is a parallel. So that is R1 parallel to R2 parallel to Ri. That's all. We'll be getting this equation. Okay. Now already we have defined this equation, right? This equation just copied from the previous slide for your continuation. See now, what I have done is V0 equal to minus Gm V pi. Okay. So I have substituted here. Now V pi is nothing but IBR pi. So your equation will become V0 minus Gm IB R pi into RC parallel to RL. So now you substitute this IB here. So your equation will become V0 equal to minus Gm will be having II into R1 parallel to R2 divided by R1 parallel to R2 plus Ri. Alright, so I have substituted this IB here. Then you have a R pi, then RC parallel to RL. Okay, so this equation you are get after substituting here. Now in place of II, if you substitute this one, you will be getting this equation. See, you can see here V0 equal to minus Gm. So this whole part will become for IA. So the remaining things, everything already defined, right? R1 parallel to R2 divided by R1 parallel to R2 plus Ri. Then R pi RC parallel to RL. That's all. You will be getting this equation. Now our ultimate aim is I want to find the magnitude, right? The magnitude is independent of your frequency because during the midband gain the reactance of the capacitors is 0. So that means V0 by VA, right? So when you take a modulus, you will be getting, okay, so this is for like a V0. So you want to find a V0 by VA, right? So divide this equation by VA. So VA will get cancelled. So what is your final equation? AB equal to V0 by VA equal to Gm R pi RC parallel to RL into R1 parallel to R2 divided by R1 parallel to R2 plus Ri into 1 divided by Rs plus R1 parallel to R2 parallel to Ri. So we will be getting this equation. So same it is given. So just put a modulus. So because we want to find the magnitude, independent of the frequency, you will be getting this final answer.